Today I'm going to talk about Tic-tac-toe game. It's also known as Noughts and Crosses. This game is very old, and I think its history reaches almost ancient times. It's very good for, especially for kids or children, to teach them logical thinking. But we will focus on how to design a program that will act like a human, that will be as effective as a human during a gameplay. Alright, for the sake of format, let's try to remind quickly rules. So in order to win in this game, you have to get 3 figures of your choice in a row. So for example, it might be vertical row. This is the winning situation. It might be a diagonal row, and it might be also a horizontal row. Yeah. The thing is that your opponent will try to block you or will try to establish a winning situation for himself. Yeah. So that are the rules. All right. So probably you know that this is the game that if you play properly, every game will end with a draw. So it's solved game. So if you have 2 players that are playing perfectly, then from given game state, from given position, you can predict an outcome, yeah, of the game. So that's the important part. All right. So let's try to think a bit about implementation. At the below in the description, you will find a link to my GitHub repository when you can download a game. It's written in JavaScript along with some Mocha.js unit tests. It's pretty simple. Okay, so let's try to think about implementation. Alright, so when it comes to game implementation, probably the most beautiful way of solving this problem would be to design kind of artificial intelligence that we could teach how to play. So this intelligence could grab some experience from us, and from play to play, it would become smarter and smarter, and at some point we won't be able to win with machine. But for now, let's stick with a brute force approach, in which we will leverage from computation power of our personal computer. All right. Having said that, let's think about this game in terms of game tree. So here we have some initial game state. So our opponent put a cross in the middle. From this state, we have 8 options. 8 possible moves that we can do as a machine. So as a machine, we will try to evaluate each possible field, yeah, and we will choose the one with the highest evaluation, the highest number, based on some algorithm. Okay, so from each point, our program will try to emulate gameplay till we have draw, lose or win. So for example, from this branch we can go here, we put a circle on the right, and from this gameplay we put a cross, and so on. So our tree develops, yeah. So at some point we might find that we, as a computer, we have won, we would lose, or there is a draw. For example, for the winning situation, we will assign a positive number. Yeah. For the lose, we will put a negative, and for a draw, we will put a 0. So, after evaluation of each branch recursively, we end up with some value here that will be a result of computation of addition of those three numbers. So, for example, we might have at this position 8, or at this position we might end with, I don't know, 1, 3, 0, and so on. Yeah? And for the next move, we will choose the one with the highest number. Okay, so this is the basic idea on how to solve this problem, and the program doing this evaluation is very simple. The thing is that it doesn't work properly. The computer is not enough smart to win with properly playing human using this approach. The thing is that it's only calculating, it's only adding those numbers. So probably this computer might evaluate winning situation as 1 when game ends here, and it also can evaluate a losing situation here as -1. So this -1 will nivellate the one here, and it will be 0, but it's not a good evaluation, it's not smart, because as you can see, this game ended with a lose very quickly here, and this game ends with win, but it took longer time. So maybe it's a good idea to evaluate the number for given play based on empty fields left, or based on the number of already done moves, yeah, on moves that are already done. So this is the one approach, and my approach was a bit different, and you will see in the code. So if I find a situation when I am as a machine, when I am losing a computer game in the very next move, I will assign a very low number or very high negative number to the game. So this will cause that the field with the feedback from this field will be highly avoided by the algorithm, and another field will be chosen. So this is a kind of defensive strategy. And of course, the situation where we can win in the very next move, let's say for example here, we can win here, and this will be priced very high. So this will cause that computer will be smart and will try to finish the game as quickly as possible. Okay, so for the example, I will show you what situation fails when you use just simply recursive approach with the evaluation 1, 0, -1. So let's imagine a board like this. Here we have the situation where our opponent put a circle here, and the machine evaluated all the possible gameplays and it obviously put cross here. In the next turn, the smart human will put a cross here in order to create a win-win situation. Yeah, he wants to have at least 2 rows that are winning. And simple recursive branching algorithm will evaluate this field as the highest field, the most prized field, yeah, and will put a cross here because it might lead him to create a winning situation. But now, what human is doing is putting a circle here, and the game is practically over, because even though computer block him here or here, he can 2 winning pass. Yeah. So this is the test case that was failing when I designed a simple branching approach with evaluation -1, 1, and 0. Okay, so I hope it was clear, and to better understand my approach, please take a look at the code. You can run this game simply by launching, opening it in a browser locally. Thank you.